Hello, my name is Tom Willemain. I'm one of the founders, along with Charlie Smart and Dr. Nelson Hartunian of Smart Software. Today we're going to be talking about regression analysis for forecasting, a specialized, more advanced technique that some of our customers use to improve the accuracy of their forecasts. Now, if you're not using regression analysis, you're probably using something called a time series method or an extrapolative method. And the difference is the time series methods are simpler and faster, but not necessarily more accurate. The regression methods can be, but also are not necessarily more accurate. So we'll see how they're used and what would make them a good choice. So let me sketch out a typical forecasting problem. There will be some variable of interest. Maybe it's sales. And we have a record of that over time. So we have a record, say, of demand for a product over time. And the data may look something like this. So it's very random looking. And the time series methods are aiming at a very simple description of this. They're trying to understand where's the middle of that noise. So they're, for instance, trying to do something like this, and then maybe making a forecast like that. And those methods consider all this zigging and zagging to be untouchable randomness. It's unexplainable. It's all the forces in the universe working on the sales. And those are just nuisance noise that has to be averaged out by the time series method. If you're taking a regression approach, though, you look at those bumps differently and you say, what if they are in fact not totally random, but at least partially forecastable? So instead of being a nuisance, there's actually information in the going up and the going down. That's the starting point mentally for why you would try to do a regression analysis. And the key step is to be able to use your substantive knowledge of your problem to nominate for consideration some extra variable, an additional variable that would explain some of that zigging and zagging, some of the randomness. So it's not really random. It's explainable if you bring more information into the problem. So you can see that that's more expensive because you need another variable, and you have to get the record, make sure it's accurate, and then find a way to use it. But if you can find another variable that is predictive of what looks like random noise, then you get a much deeper understanding of the problem, and you can make more accurate forecasts. Whether you can do that or not depends on whether data are available, whether you can use your subject matter expertise to find that variable. So what we will do instead of this picture is make a somewhat different picture. We will try to find another variable which is related to sales. So maybe it's sales and maybe it's, say, temperature. Maybe you're selling something like ice cream, and when it's hot you have more sales, and when it's cold you have fewer sales. So now each point in this time series becomes a dot in this graph, because at a certain day there's a temperature and there's a sales level. And by looking at two time series and making this sort of a plot, we get what's known as a scatter plot, relating observed values of temperature to observed values of sales. And if you see a picture like this, then you've got something. Then you have leverage to use a regression model to seize this information and refine the forecast of sales, because there's, besides all the forces in the universe that are affecting the level of sales, there's one in particular which may be powerful and knowable and exploitable. So that's the approach we take to regression analysis. And what we'll do with the regression model is say, Here is an approximation to that relationship. So if you give me a particular temperature, I come up to this curve and I can read off a particular projected sales value. So we need to find this line, and then we can exploit that relationship. And if we're just looking back at history and we want to explain to ourselves when is sales higher, when is sales lower, and how does temperature affect that, this picture is the answer. If we want to go further and forecast sales, then the regression approach puts an extra burden on us. Here, with this picture, the time series approach, we can find some way to extrapolate or extend this orange curve. Maybe we're going to make a flat forecast based on the current estimate of where the sales level is. Here, to make a forecast of sales, we have to have a forecast of temperature. And that's turning a single forecast problem into a double forecast problem. But if temperature is related to sales, and if temperature is itself forecastable, then a regression approach can improve the accuracy of your forecast of sales. And what will follow now is some more technical stuff about how you find this line and the three types of regression models that are commonly used in business. One is called autoregression, which is a special case where this second variable is actually just old values of the thing you're trying to forecast. So you might forecast sales next month from sales this month. So that gets rid of the problem of having to find two variables and to forecast the second one because you're just using known values of the first one. That's autoregression. The second of the three alternative ways to use regression is called a causal model. In this case, for instance, we believe that the temperature changes have a direct influence on the sales. They cause changes in the sales. And then there's a third, which is a variant of that, where this variable, the one we're predicting from, is not the same as this one, but it is a leading indicator, meaning that the values of this other variable in the past, not forecasted but already known, can be used to forecast sales. So that too is a way of avoiding the double forecasting problem. So we'll talk in a minute about how you get these lines estimated and about the particular technical details of autoregression, causal models, and predicting from leading indicators. Now that we've seen the overview of what regression analysis is about and how it's different from the time series forecasting methods, it's time to put on your seatbelt. We're going to have an equation or two, and we're going to talk about how you find that straight line which relates one variable, like temperature, to the one we're forecasting, which is like sales. So let's put that picture up again. We have temperature and we have sales, and we have we've got a record of the simultaneous values of temperature and sales, and we're finding in general that on higher temperature days we have higher sales. So that's where we were before. We're going to call this the response variable, and we're going to call this the predictor. It sort of makes sense. So temperature is a predictor of a response, which in this case is sales. And we said that the essence of this approach is to find a straight line, which is a mathematical representation, which is trying to distill the message in this picture. This picture is called a scatter plot. This line is called a regression line, or a best fit line. The term regression has strange historical precedents back in the early 1900s. So this line, if you remember from high school algebra, a straight line has an intercept and a slope, and it has an equation. And so we'll, in general, call this y and this x. We're predicting y from x. And the equation is that y equals intercept plus slope times x plus error. In other words, there's still some variation around this line. It doesn't explain everything, it explains part of the randomness in the problem. And if we make this mathematical, we could say this is y is alpha, just some number, plus beta, another number, times x plus error, epsilon. This equation codifies the relationship between the predictor and the response. Alpha is a number, beta is a number, and x is all else, all the other factors besides x which have an influence on y. And those are responsible for these variations around the regression line. And so this is the general theoretical model. What we will actually estimate is that y is some particular calculated number a, the intercept, plus b, the slope, times x. And we'll say this is the prediction of y hat given x. So how do we calculate a and how do we calculate b? The computer, of course, will do that heavy lifting to calculate a and b, but the principle is very simple. If there's a particular intercept and slope here, if we extended this back to where the temperature is 0, this would be the alpha, and if we go up by 1 unit in temperature, the slope would be beta. So that's what they mean visually. How we would calculate it is, we would look at the actual scatter plot. Let me just approximate it again like this. This is our data, and we would try out different values of alpha and beta. For instance, if we said that straight line is a good summary of the relationship, we would say you're crazy. The intercept is too low and the slope is too high. It doesn't fit in the middle of the data. Likewise, this was also a very stupid line. It tilts the wrong way. But this line is probably pretty good. So the principle we use is to see which line comes close to the actual data points. And I'll erase this and start with a cleaner picture, and we'll just look at how we would calculate the intercept and slope. So let me redraw a representative scatter plot. Here's y, which is the predictor, and x, which is the response. And we're going to imagine that we have a data set that looks something like this. And we're trying to find a straight line which, in a particular mathematical sense, comes as close as possible to all the data points. Now obviously you can't put a straight line through and touch all the points. There's still the randomness in here that moves it off any straight line. But you can come up with a reasonable approximation, which by eye might be this. That could be it's a decent looking approximation. Now, what makes that a good answer? A good intercept and a good slope? Well, it all depends on these errors that we make. At each point, for a given x, we're expecting y to be the value that's on the green line. In this case, it isn't, right? There's this gap. That's called an error in fitting the data. And for every data point, there's an error. Sometimes the error is very small, sometimes it's bigger, sometimes it's positive, sometimes it's negative. So we have all of these discrepancies or lack of fit between each data point and the regression line. So what we want to do is say, let's try to get all these little vertical stubs, the red lines, as small as possible. Now, if we tilt the line, say, closer to this one, we can make that error smaller, but we're going to, for instance, make some of these other errors bigger. So we don't want to try to fit one particular data point. We want to come close to all of them, even though we might not exactly hit any of them. And a way to do that is to say, let's look at every one of the errors and total them up. That will give us a summary of all the errors we make, and we might want to keep that small. And that's almost a good idea. We could take, we could say the error is each y minus each x, and we could add those all up. And the problem is, some of them will be positive and some of them will be negative, and so they'll offset each other, and they'll kind of cancel each other out. All these that are above the line are going to be matched by some that are below the line, and it'll just say, well, you're close to the total, but you could be far off for everything. So there's a little trick we use. We square these so that the negatives, like if we're off by 3 in the negative direction, it becomes a +9. And if we're off by 3 in the positive direction, that's also a +9. So it's just the distance, not the negative or positive sign, that matters. And then we will just add up all these errors over all the points, and that becomes our criterion. We want to minimize the sum of squared errors, and that is naturally called least squares regression analysis, where you pick the intercept and slope so that the sum of the squared deviations between the data and the model, the green line, are as small as possible. And you say that's a good answer. And that's the one that the computer would calculate for you. So it's possible to have more than one x. So instead of a line, we might have something like a plane in 2 dimensions or 3 dimensions. But the principle is the same. We want to put that line or the plane as close to all the data points as possible. We find the sum of squared errors, and we minimize that by jiggling the intercept and slope until we get as small a number as possible. Now, we don't actually jiggle it. You can, those of you who remember your calculus class, you can use calculus, and particularly derivatives, to write an equation or a set of equations for what the intercept and slope should be to make this quantity as small as possible. We're not going to do the calculus here. This is already kind of mathy for most of our audience. But that's what's happening. We're finding the green line close to the black points by making all the little red stubs as small as possible, ignoring their signs. So that's the hidden mechanics inside the application. We'll finalize this talk by explaining the 3 different ways that we can use regression in a practical business problem. Okay, if you're still with me, we're on the final leg. We're going to talk about 3 different ways that regression can be useful in a business forecasting situation, and I'll list them here. The first one we'll talk about is auto-regression. The second one is causal modeling. And the third is called leading indicator regression. And these are all basically just variants of regression analysis, but they have different data requirements and different levels of work. The auto-regression, you can tell in the name, is regressing the variable you want to predict on itself earlier in time. So the auto-regression is if we're going to predict y, let's suppose the current time is capital T, and we want to think about where will y be at a future time, at some forecast horizon h, like 1/4 from now or 3/4 from now. So y at capital T plus h, we're now at capital T. We want to go forecast horizon h ahead, maybe 3/4. We want to predict that. And the model we can use here is we're going to have an intercept plus a slope times something. And the thing we're going to use now is y at t minus h, t plus h minus 1. So this would be at not 3/4 ahead, but 2/4 ahead. And so we're predicting y from a slightly older value of y. And to show how this would really work in practice, we would start by going 1 period ahead, and that would mean we want to predict next month's y from the current observed value of y. This is known. It doesn't have to be forecasted. This is being forecasted. So we would make our plot showing the data now and the data in the next observation. There would be some sort of a relationship like this. Here's t and t plus 1. We would get this sort of plot. We would make the regression line, find the intercept alpha and the slope beta, and we would make our forecast this way. So that's very simple. And if we wanted to do the forecast for t plus 2, we'd use the same equation. What are we going to use for the value of y at t plus 1? That's a forecasted value that we've already made. So we would forecast, take the output from our last equation and make it the input to the next one, and we could keep stepping along like this. It would sort of bootstrap its way along. So we go 1 ahead based on now, and then we would use that 1 ahead to forecast 2 ahead, and the 2 ahead to forecast 3 ahead, and so forth. We chain along. And that's auto-regression. So it's nice compared to the general case because you don't have to have a second variable. There's no x. You've got one data series of the, for instance, the sales, and you use the relationship between consecutive months of sales to codify that into a regression equation and then to stretch out a set of forecasts. Now, the second approach is causal modeling, and that's just really the one we talked about at the beginning. We want to forecast y at some future time, say t plus h, and we're predicting it, and we're going to have a regression equation, and we're going to use some x, some other variable, to predict it, but that variable has to be known at a future time as well, because they're always measured at the same time. And so we have a separate problem. We don't know x of t plus h any more than we know y at t plus h. So we'd have to have a separate equation to predict this. So there would be a separate equation predicting x, and whatever that forecast was would be the predictor variable. So this forecast predicts that forecast. And this is obviously more complicated because you have a double forecasting problem, and you need to figure out what x might be. And often, if you sit around with experienced people, they could nominate maybe a short list of possible x's, and then you could do a little data detective work and say, well, maybe temperature affects sales, maybe price affects sales, maybe promotional activity affects sales, maybe all of them do. But you could look at them one at a time and see, make a scatter plot of y against, say, the first possible x, and y against the second possible x, and y against the third possible x. And if you see something that looks like this, you're out of luck. That x doesn't have any leverage to forecast y, so that's a bad one. If it looks like this second possible x is a very powerful predictor, because that regression line is pretty close to all the observed data. So, and this other one might be something like this. there is a relationship, but it's kind of weak. So if you're only going to use one, this x2 is the best choice among x1, x2, and x3. So that's using causal modeling, where we're saying that this x actually causes. We can tell a story that says, if I promote, if the temperature goes up, if I lower the price, there's a theory about why that will affect y. It will make y change. It's causal. And so if you can predict the driver of y, the predictor of y, you have a nice mathematical approach to codify that. And the final of the three is this leading indicator regression. And if you can find a leading indicator, it's worth its weight in gold, because it's causal modeling without having to make a second forecast. So what is a leading indicator, and how would you detect that you have one? Well, it's simple. If the leading indicator wiggles, after some time the response variable will wiggle. Maybe it'll go up, maybe it'll go down, but they're linked. And because of the time lag, excuse me, you can take known values of the leading indicator and leap into the future through the regression equation to make a forecast for the response. So what that would look like in terms of time series, for instance, is suppose that we have the two variables. We have the response and we have the leading indicator, or what we think is a leading indicator. So the response might be, I'll exaggerate here, maybe the response does something like this. And so we see that something is influencing this and changing the value. Now if it turns out that the leading indicator was doing something like this, we see the same sort of pattern after some delay. This happens, then that responds. This happens, that responds. This goes down, that goes down. This goes up, that goes up after a while. That's the picture that would give us a leading indicator, an indication of a leading indicator. So if you're in this situation, you've got a very useful leading indicator, and if you convert these into a scatter plot, it would be y at time t and x at time t minus L, say, for the lag, where this is the lag, L. Maybe the leading indicator changes and 3 months later there's a response in your sales. In real life, how might this work? A classic example is, suppose that you make sheet glass that go into windows and doors. If you have a record of housing starts in your area, in your sales area, you know that if somebody gets a permission to build a new apartment complex, after a certain number of months they're going to need windows and doors, and you're going to be able to sell glass for the windows and doors. So it's a simple and classic example of a leading indicator. The housing permits, or the housing start information, is a leading indicator of the sales of your glass. And the graphical picture of the two time series might look something like that. And the scatter plot would look like our familiar kind of situation, only this might be, for instance, this particular point might be y at time 10, and it also might be x at time 6. And so in this case, L would be 4. There's a 4-month lag between the cause and the effect. But that's the only difference. Once you're in this situation, you know, it's just the mechanical problem of finding the regression line that summarizes that data relationship. And you will have a forecast of y at a future time. Let's say t is now plus L is alpha plus beta times x at time t. So this is known, and it'll predict L periods ahead. And if you wanted to go one period ahead, it'd be t plus 1, that's just going to be alpha plus beta x of t minus L. So this sort of relationship is just like causal modeling, only you have the luxury, at this particular time, you've already seen this. You know what this value is, and so, I'm sorry, if you're at this time, you will know what happens after L, and if you're right here, you'll know what's going to happen out here, L periods ahead. So that's a leading indicator type of analysis. So to summarize then, regression for forecasting starts by saying all those random bumps, the little zigs and zags, some of that may be predictable if you have more information. And the more information might either be old values of the thing you're trying to predict, that's autoregression, or it could be another variable which causes the predicted variable to change, but you have to forecast that other variable too, that's causal modeling. Or you found a leading indicator which is a causal driver, but you don't have to forecast it because you can look back into the known record to get the values for X to plug into the regression equation. That's leading indicator forecasting. So all of those are ways that we can use other information beyond the time series approach to possibly make more accurate forecasts of something that we care about.